Then welcome to the 12th lecture in Introduction to Lattice Boltzmann methods. We are coming closer to the end of this term, of the semester. And today we have kind of advanced topic. Okay, we only have advanced topics in this lecture, but today we are talking about the efficient implementation particular of the cumulant method, and the content here is that we are talking about floating point representations, pairwise summation, and what we call the Chimera transform. So efficiency, of course, has several levels. Yeah, we could talk about efficiency in the Lattice Boltzmann method, where we would in particular talk about how to merge streaming and collision. Yeah, should also be a topic. But today we are not talking about the algorithmic efficiency, but the numerical efficiency, if you will, and you will understand what I mean by that. Okay. So the Lattice Boltzmann method, as we've learned throughout this lecture, comes in different versions. For example, the BGK single relaxation time version and the MRT version and the cumulant method. And what I've put down here with the Reynolds number is the Reynolds number per grid spacing, so to speak, that we can actually reach with such a method, and we still get a physically reasonable result. So what we see is that the single relaxation time method is gets a little bit beyond probably the Kolmogorov scale, if you will, but is less efficient than the multiple relaxation time method, and there's a big gap between the multiple relaxation time method and the cumulant method in how coarse, so to speak, the resolution could be. Yeah. So, but of course there is a price to pay, which we are willing to pay, namely that this method here, the single relaxation time method, is pretty cheap to compute. The multiple relaxation time method, because it has more operations. Here it goes streaming distributions through moments collision and back. It's more expensive, and the cumulant method is yet more expensive. And now we are talking about what is going on in these transformations here, and how to make them efficient, because in the beginning of the cumulant method is actually quite interesting. The cumulant method was already known for a while and didn't really work, yeah, because it was numerically difficult it is numerically difficult to actually compute cumulants, yeah, because they are not, as we say, not well conditioned. So if you just look at the equation and you write down the equation, you will end up at something that kind of works for simple cases, but you will not see any improvement compared to these other methods, unless you really think about the stuff we are talking about today. Okay, this is not working. I've written down a few observations about the methods, yeah, so I will upload them later. Just let me read. So the number of floating point operations per node update in the cumulant method is relatively high when we compare them to these other methods. This is what I just said. And another thing that we are not talking too much today is that efficiency is nowadays more governed by the memory access. Yeah. So when I was little, yeah, there were already computers around, and we said that operations are very expensive, and then there is RAM, that is random access memory, because you can access anywhere and it's all the same expensive. This was before the invention of cache and pipelining and all these stuff. Yeah. So then nowadays, getting your data into your processor is the big problem. Processing the data is usually not a problem. And this is important in that context of the cumulant method, because what it means is that even though there are so many more operations that you have to do, it is not proportionally more expensive. Yeah? Because what is written down here is that usually the Lattice Boltzmann method is limited by the memory access. Yeah? So the memory access, so you have a lot of data that you have to read, then you have to do a few operations, and what slows you down is getting the data into your processor. So doing more operations will not usually for a while, say, let's say comparison between BGK and MRT, you will hardly see any difference, even though MRT does more operations, but not so much more, yeah. And the expensive part is the reading of the data, yeah. And by the way, you can also use something that is called communication hiding. You probably heard this. No, the communication hiding is the idea that you could also call it compute hiding. Yeah? So your computer has to do two things. It has to read data from memory, and it has to do the computations. And there are caches in between. So what you can in principle do is you can run a computation while you are reading the next data, right? And this is what we call hiding. So they do both of them at the same time. Yeah. So and the idea is that your algorithm is kind of optimal if both of them are balanced, in the sense that you do as much. So computation takes as long as the reading, so they can just. So nobody is waiting for the other. Yeah. So when the computation is done, the next data is there. Yeah. In that sense. And so with Lattice Boltzmann in our modern hardware, we are kind of at the boundary. Yeah. So we are relatively well balanced. And what is with BGK, it is usually the way that memory access is more expensive than computation. So computation actually waits for the memory. Yeah. And in cumulants, it is such that the memory access has to wait for the computation, because computation is so much more, yeah, that we actually this becomes dominant. But it is close to the boundary, and because it's close to the boundary, it is very useful to think about how we can optimize this a little bit so that we get to a well-balanced algorithm later. Okay. And then there is another thing that is often ignored if you give the task of implementing Lattice Boltzmann code to a computer scientist. So the computer scientist thinks in algorithms and whether this is fast or slow. Yeah. And if you think from a mathematical point of view, there's another problem with all of this, namely, you got of course round-off errors due to the computation, and this is the problem that I just tried to address in the beginning. If you have more operations, then you get more round-off errors. Yeah. So this is like computational erosion, and this computational erosion is stronger in the cumulant method than in the BGK method, because there are more computations one after the other. And this may actually lead to a condition where mathematically cumulants should be better, but in reality BGK kind of nails it because it has less round of errors. Yeah. So this is of course a problem that can be solved and has been solved, but this was the original observation with this kind of model. Yeah. That it was not convincingly better, say. Yeah. Okay, but now it is. So this is why we are going to spend some time in understanding round-off errors. So understand round-off errors. And now there is two components. One is the actual computation that you do, and one is the representation. Representation means the size in the storage, and this is what we start with. Yeah, we look at the data loss just by storing data. So we have these populations that we store. So the population Fijk, now we are in 3 dimensions. So what are they? These populations are essentially, one of these populations comes out of all the moments that we have, yeah, in different ways. So what we can essentially say, this is a superposition of all the moments. And the moments we call MABC. So basically you can usually write things like this, Fijk. So there's a back transform, yeah, which can be written like this. You are summing over all the moments, and then there would be a tensor, call it alpha ijk ABC, and you multiply by ABC. We are not specifying this tensor, but you can write this as a kind of transformation matrix, right? Here comes the moments, you multiply by this thing, and you get out the distributions or the populations. So, and now these populations, so, okay, what we established is each population is a combination, in one sense, of the moments, right? So you sum them up with some coefficient, right? So this is how it works. So, and now after we put our moments in the populations, we are going to store them in a floating point number. And we often do this in double precision floating point numbers, but not always. For example, double precision floating point numbers are expensive, and in particular, if we work on, so to say, modern hardware like GPUs. So GPUs don't like it when you do your computation with double precision floating point numbers. They prefer single precision floating point numbers. Yeah? So then they are much, much, much faster. So this is the question, can we actually do this with single precision floating point numbers? It's of course always better to use double precision floating point numbers from an accuracy point of view. So how does a single precision floating point number look like? And by the way, everything I'm saying here is the same for double precision floating point numbers too. It's just that the size of the system is larger and the problem therefore is smaller. Yeah, but still the problem exists. So there is a standard IEEE 754 they describe both 32 bit and 64 bit floating point numbers. So in order for me to have it a little bit easier, we're just talking about the 32. And we would also prefer to have our method in this regard. So how does such a floating point number look like? I'm just 3 times that's yes. Okay, I'm just guessing the size. So say this here is 1 bit. So these are the bits, yeah. So there's 32 bits, of which 1 bit, first bit, is the sign. So it's just saying whether this is a positive or negative number, yeah. And then there is 8 bits for the exponent. So because it's a floating point number, yeah, it can have different exponents. So in order to move the point, yeah, the floating point. And then it has the so-called fraction. It's called, I think is it also called mantissa? So, but this is the fraction. So this is the once you know the bit, once you know the leading bit or the point you moved your floating point number to, or the point of the floating point number, yeah, in the beginning. So there is this 1 point, yeah, and then you can have 23 bits after this, right? This is how data is generally stored. So, and now what we need to do is we have to put all our moments in this, and we have to understand that all moments share the same space. So, by the way, this is a kind of different in the Navier-Stokes equation, where you have and they're all in the fraction, the same space in the fraction. So in the Navier-Stokes equation, you have the pressure and the velocity in separate variables, right? Here we lump all of them together in one distribution. Yeah? So you put everybody in one room, so you hope they like each other, right? So do these guys like each other? It turns out they don't. Why don't they like each other? This has to do with we can understand this by using our asymptotic analysis. So according to our asymptotic analysis, we have moments, or the moments have different scales. Okay, we can do this in diffusive scaling or in acoustic scaling. Let's say diffusive scaling is the correct one because it converges to the Navier-Stokes equation. Let's use diffusive scaling, where we say that delta t is proportional to delta x squared, and this we say it's proportional to epsilon, our smallness parameter epsilon. So now the different moments in here come at different scales. For example, at the scale epsilon to the power 0, yeah, so scale order 1 directly, we get the density. Yeah, the density, which is rho to the 0 order. Yeah, so this is 0 order. In epsilon 1, epsilon to the power of 1, we get velocity. So we have epsilon u1, and then we have epsilon, for example, epsilon square. We get the pressure, epsilon square, and the delta, so the change in density. Yeah, so this is actually what we what we are taking the pressure proportional to. Okay, I mean, the pressure is, of course, there is a background pressure given by the density rho 0, yeah, but we are only, from Navier-Stokes' point of view, we are only interested in the variation of pressure, not the pressure itself. Yeah, so in the variation of the pressure, this is second order. This we learned from the asymptotic analysis. So, and then, of course, you know, we get these, just to remind you, the physical velocity, or the numerical velocity that we have, yeah? This is a combination of the actual solution. Say this is the solution. And the associated error, and the leading order error here would be, because it's a symmetric method, would come with epsilon cube and cubic order. Now it's working. And that would be the error. So this is something that we actually would prefer not to have, right? But we'll prefer to have these velocities. So now we have to understand, we have not directly specified what epsilon is, but epsilon depends, of course, on the simulation. But the thing we are sure of is, asymptotically speaking, epsilon to the order 0, so 1, right, is much larger than epsilon to the first order, is much larger than epsilon to the second order, and so on, of course, right? So this is what we established. So this means these variables we are talking about, and they all be stored in the same floating point number, they have a separation of scales, which sometimes is good, and in this case it's bad. So the variables are, we say, scale separated. So scale separated variables, but they share the same space in the fraction. Okay, now we have to draw a picture in order to understand what that means. Say we have okay, so this is our fraction, right? This here is the fraction. And here in the beginning we have the most significant bit. And here in the end we have the least significant bit. So what does it mean they share the same space in the fraction? So the floating point number is made up of, okay, sign, yeah, exponent, and then fraction. And it can have only one exponent, obviously, right? So the largest contributor to this just sets the exponent, and all the others have to fit in with this exponent, right? So this means in the largest contributor, so let me say this is the fraction. Okay, maybe it's better to write this here. Okay, so the largest contributor is the one at order 0. This is this rho 0, right? Rho 0 comes, let me draw this like this. Rho 0 is stored on all the bits. Yeah? It has 23 bits available for just storing rho 0. Okay? Now, where is where's the first order? Say first order is U. U is first order. This is, say, here. So, and this means, because the exponent is given by rho 0, yeah, there is less space left for U, which means we have this space for storing U. So, I mean, this is of course completely cartoonish now, yeah? So, okay, this is a variable of first order, so where do I have to draw second order? Yeah? Second order, so if I have here a gap, which we've not specified, but it is smaller, then second order, which is of course related to the, what is it, theta times delta rho to second order. So this is one thing that is second order, and another thing that is second order is also the derivative of U, so the non-equilibrium second moment, yeah? So equilibrium second moment is this thing up here, and non-equilibrium second moment, yeah, has the same order, okay? And they must be roughly, asymptotically speaking, as far distant from U as U is distant from rho, right? So then that would be roughly here, and this means that the available amount of bits for storing this looks like this. And then we have the actual ghost moments, so ghost moment, or the first order ghost moments, or the third order moments, which are the first ghosts. So they again are as far removed as they are again as far here, so this is, say, ghost of third order, and you see they have even less. So, in a sense, I noticed that I've drawn this picture a little bit too optimistic. In reality, we often see that the ghosts are very much at the end of this line, and that is very, very badly represented. Yeah. So, but this, of course, depends on what you're using. If you use a double precision number, yeah. So this range that you have available here is much larger, right? So then, and so to the, say to the, it is larger to the right, so the least significant bit is smaller. Yeah. If you use lesser precision, you move the least significant bit further to the left, and you could also use 16-bit. Yeah. Then you may actually cut off some of your moments. So what we are seeing here is, so to speak, the effective bits available for each quantity. Okay, let's do an example to try to understand this. So rho 0, so this is always 1, right? So then we have to choose a velocity. So we know that this is the CFL condition, which dictates us velocity must be smaller than 1 minus square root 3 at square root 1 over 3, sorry, right? At all times. And so when we want to have it at all times, then we have to make sure that it needs to be considerably smaller, so that still when we have vortices and turbulence, it always stays smaller, right? And the other thing is, You know, we have gone to school and we learned you make your smallness thing smaller, so make your velocity smaller, means larger time step in a sense, yeah. Then you get a more accurate result, yeah. No, so this lecture here just shows you that you have been lied to, yeah. So yeah, you would usually do your velocity smaller, your lattice Boltzmann velocity smaller in order to what means you have a smaller time step because you have been told smaller time step, more accurate result. This is what asymptotic analysis tells you. And now comes the ugly reality, right? So let's look at the ugly reality. So we say that u, say, would be 0.01. So this is actually not a small velocity, right? Yeah, that's not really small. Yeah, and delta x by delta t. So if this is your velocity, then for example, the third order part, we don't know what exactly it is, yeah, but it now should be of the order of u square, right? So if it's of the order of u square, what we expect is that it's 0.001. Yeah, in that range. It's not exactly, yeah, but in that range. So then we know from above that rho 0 is largest and defines the exponent. Of the float. So float is a shorthand for floating point number. That means that this rho 0 gets all the 23 bits, yeah, all of them available for that. So of course this is pretty simple because it only needs let me see. So, okay, I'm actually trying to write this down in binary numbers. So there's one point which is implicit, then there's 3 0, 3 0, 3 0, 3 0. So this was 4 of them. 1, 2, 3, 4. So n binary. Okay, I hope I didn't make a mistake. So this is how the thing is stored, yeah, in binary numbers. So it's either 1 or 0, right? So this u is stored according to that scale. So what we actually have to do is we have to.
And is more than like 23 bits?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So it's 20. So you know the leading one is implicit. Yeah. So this is okay. It's always one more. Yeah, because you don't need to store the leading one, because you know that there need to be a 1 at this place, right? So this is why you have one more. Okay, so you have to divide u by rho, which is easy because it's 1, right? And this is then 0.01 in decimal numbers, and this becomes 0. So there's 0, 0, 0, 0, 0, 0. Okay, I hope that what I'm written here is correct. I just copy it. It's also not very important. 1, 1, 1. 1 0 1 1 0 0 0 0 binary. So what does this mean? This means that here would be 7 bits. Yeah? And they are not available. I mean, you could of course say the missing bits are down here, but we shifted. Yeah, we have a fixed size. So if we shift this down here, so we've lost 7 bits. Okay, see, take the velocity was not very small, 0.01. Yeah, this costs us 7 bits out of 23. Okay, so this is absolutely significant. Okay, let's look at the second order terms. So let's have the variation in density, which is the pressure. So we'll get to 1.0001, and that would look like this. I hope I'm doing it correctly. So I said that, okay, I'm 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I think that's it. 1, 1, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1. Okay, so here we got rid of 14 bits in our pressure. Now you have to pause a little and think about this. You have 23. That's more than half of it. Is like, I mean, say lost, it's generally unavailable. Yeah? Because it's everywhere not available. We have not done any computations with it. This is before computations. It's just not possible to know it, no matter how exact it would be measured, it would be computed, it's just not there. Right? More than half of the bits are lost. And the velocity was not small to start with. So in this case, 7 bits of the fraction are lost at each order. So I mean, this is of course going on to the next order. Of epsilon. And of course, the number of bits lost depends on the magnitude of the epsilon 1 variables. So, for example, this is U1. Now, as I said, we were told make this time step small so you get more accurate results. You have to keep the following in mind. The smaller the time step, the smaller u in the units, so the velocity u in units delta x by delta t, because we have to express them in delta x by delta t. The even smaller are the moments points of higher asymptotic order. So you see, if we started from an even smaller time step, we can easily get like, if we just a little bit smaller, then saying we lose 8 bits or we lose 10 bits, say we lose 10 bits in the velocity, yeah, then we lose 20 bits in the pressure, then we have, you know, three bits left to describe our pressure. How accurate is this? It looks funny, yeah? So you can implement this. I don't have code left on this, so we destroyed it. Yeah, but I have seen this where pressure just completely disappears because you're trying to do an asymptotic a convergence test, yeah, with higher order, smaller time step. And now pressure disappears, yeah, because single precision, yeah, and you have 3 bits of describing your pressure. It looks very funny. Okay, so let's make a small back on the envelope thing. What is the maximal ratio of the smallest to largest variable? I mean, this doesn't make a lot of sense, but just for, you know, just for getting an idea. Yeah. So if the smallest variable is represented by a single bit. Yeah, so it's up to you to think whether this makes any sense. But say the smallest variable is just a single there with a single bit. A single significant bit for the smallest variable. Smallest. So this is 2 by the power of course, 23, right? And this is 838,000. No, sorry, wait. 8. What did I say? 8,388,608. So, for example, now if we make it small, say this is rather small, and say it's 10 by the power of -4. Yeah, so that would be velocity 10 by the power of -4, then this here would be rho delta. So the density here would be 10 by the power of -8, which is already much smaller than this. So basically, one variable can be 8 million times bigger than the other. Okay, is this a lot or not? Yeah, here it's no, not bigger than the other. Okay, sorry. This here is the ratio that the largest variable in this case would not be the velocity, yeah, but it would be the density, yeah, the background density. So, for example, if we have this velocity here, 10 by the power of -4, then the pressure would be completely unrepresentable in floating point numbers. Yeah? So let's put it this way. And also, also their non-equilibrium part would be unrepresentable. So flows with velocities smaller than 10 by the power of -4 delta x by delta t have no detectable variation in pressure. Okay, one way, of course, is don't make your time step too small. Now, what is the solution to this? Have any idea how we're going to solve this problem? No, okay. Then we talk about conditioning. Okay, we're talking about conditioning. So what is conditioning? This is maybe a little bit a flimsy definition of conditioning. So mathematicians, please shut your ears up and it's more intuitive. So conditioning is the reformulation of a problem with the aim to reduce round-off errors, or what we call numerical erosion. Numerical erosion due to rounding. So there is many things that we can do. At first, okay, just what I've been saying here. So if we say something is poorly conditioned or poor conditioning, then it's in a format that promotes round-off error, so to speak. Yeah. So poor conditioning, if you don't take care about this, then this may result in a decline of accuracy at higher resolution, especially at higher temporal resolution, but also in higher spatial resolution. Temporal and spatial resolution.
What does temporal resolution mean?
So temporal resolution means how much time steps you have. This is the temporal resolution. Yeah. So if you have in 1 second you have 10 time steps or 100 time steps. This is the resolution in time. So the good thing is, conditioning is a science that we can give an entire lecture series on. Yeah. The good thing is the simple things are the best. And then there are advanced things which improve a little bit, but no longer so much. So, the first step is the biggest, and then you just get little steps. So, and here it's the case that the simple thing has the most effect. The simplest measure to improve conditioning. What am I writing? Conditioning. There also the most effective. So, now we start with the most effective thing of all of them. And that is, we look at this rho 0. Yeah? Rho 0 is a constant. Why on earth do we store it? Right? So, rho 0 is by definition constant. So this is the single most important thing to do, to get rid of this guy. Okay, so what we do is we define delta Fijk as Fijk minus Wij, where Wij are the lattice weights. So these are the things that when you sum them up, they come out as 1. Yeah? So if you eliminate this constant part, they will be gone. So this here this the sum over I jk Wij is just this 0 part. Okay, now they are gone. Now instead, we are storing the Fijk. We don't store Fijk. Yeah, and let's look what this means. So we get a new fraction, and we have here the missed this. Okay, so this is the most significant bit. Let me just go back because there are large enders and little enders. Okay, yeah, large endian, a big endian and small endian. Yeah, so this is whether you start with the most significant bit or with the last significant bit. Yeah, and when the power processor was around in the 90s and in the beginning of the 2000s, then you had the Intel processors and the power processors, and one of them was big endian and the other was little endian, so they were data was always completely incompatible because all data was flipped around. Okay, so now we say the most significant bit, we put this in the beginning, yeah, and we put the least significant bit in the end. And now rho is gone. So the constant part is gone, which means that the first order part ends up here, which means that velocity gets all the bits. Great, isn't it? So, and then we got, say, epsilon square theta rho to second order. So this is here, and the ghosts of third order ghosts are here, and then you see we have more space left. So this in the effective available. Okay, this is the most important thing to do. And there is another important thing to do. So I remember I taught this to a student that I had in China, and yeah, okay, do this. And now what he did is he stored the data, and because he didn't know how to do the collision operator with this delta f, after retrieving this delta f, he added 1, right? Which, of course, with this one operation, you kill everything. Yeah? So, meaning you are storing it, you have to keep a chain of such storage with really without any break. Yeah? But it's always like this. Yeah? You cannot turn it back to F anywhere and try and think that this would still work. Yeah? So it's that's really important. It is essential really essential that is what we call well-conditioned. So because this is no longer poorly conditioned, now it's well-conditioned. That the well-conditioned state is preserved throughout all computations that you do. Actually, this can sometimes be pretty tough. Yeah? So you have to do the algebra beforehand, yeah, to get rid of this constant part. Yeah, because this is okay, I'll write the other one too. The accuracy, because this was now only the storage, yeah? And now you also have to do the computation, but the accuracy of the entire simulation, this is limited by the big the operation with the least accuracy. So let's just keep in mind the chain is only as strong as its weakest link. Okay, can you tell me why the guys from the guys doing finite elements never talk about this? Are they stupid? Don't they just know? Okay, better not saying they are stupid, and they are not stupid. No, there's a reason it's different. You know, the reason there is really different. Yeah. So, because why don't they care that much? They care a little, but not that much. Because their solution methods are iterative. Yeah? So, meaning if you make an error, yeah, somewhere, so the next iteration will iron this out. Now, with Lattice Boltzmann, we saw, oh, that's nice. This doesn't need any iteration. It's completely explicit as algorithm. Yeah. So there is no iteration. No iteration means there is no way, if you once made a mistake, to ever iron this out again. Yeah. This is why this method here is very sensitive to this kind of problem, whereas other methods that use iteration are not so sensitive. On the other hand, this here is very fast, right? Because it does not have any iterations. Yeah? So it touches each data only once, and then it has to get it right. Okay. Now this part, which was more than half the lecture, was just about storing data. Now we come to computation. Yeah? Now we do actually the operations. I mean, computation is, of course, where the round of error happens, right? So, okay, let me make one statement. In principle, we should do everything with the well-conditioned case, but this is a bit complicated, and what we want to understand for this, it doesn't matter. So for clarity, we use the unconditioned, so the normal way of doing it, computations. And then you know that in reality, you have to do both conditioning and using the right operations. So, meaning we are just working with Fijk and not with delta Fijk below. Yeah, so just to make the thing simpler. Okay, so given we have this, and now we are naive, and we have to do some computations. So one of the first computations that we usually have to do is, of course, computing rho. Yeah, this would be the first computation, and then the second computation would be computing the velocity, right? So let's say, so naive computation of the velocity. Okay, so how do we naively compute velocity? Say u1. So first we already have to compute the density, because we have to normalize this by density, otherwise we get the momentum. Yeah? And then we have a D3Q 27 lattice, so we go with the indices ijk from -1 to 1, and we sum over I, f, I, j, k. Yeah, so this is of course D3Q27, right? So this is how it's defined, right? So we have this sum. So actually we have three sums, and we go over all the three sums in some way. And yeah, so this is what we would usually do. So the thing is, we are summing. We have a summation over 27 numbers. Actually, we have a little less, because this I is sometimes 0. It's 9 of the 27 times, 9 out of 27 times it's 0. So we can say that of which 9 are 0. So of course you recognize, so we should actually leave the guys out that are 0. Yeah? Just not because they have round-off errors. They don't have round-off errors. It's just that they have unnecessary costs, obviously. So, but other than that, I mean, other than leaving 9 of them out, can we do this any better? Okay, so what we have to understand, okay, I'm just informing you, because we are not going to the full analysis of this, but summing n numbers has round-off error proportional to n, so n operations, yeah, times delta with this delta being the least significant bit. Or the value, say the value of the. So what we already see here by just computing the velocity is that that's not the only one. We have other moments, yeah, but the computation of these moments always are done in this as sums, right? All the moments are given as sums. Computation of them. They requires many sums like this. So we're always making sums. By the way, I had to teach this to some, or I had to tell some professors in this, because I think this is not completely obvious. From a round of error point of view, the dirty operation is the summation. Yeah? Multiplying two numbers doesn't generate a lot of round of error. Summing two numbers, especially if they are not same size, yeah, this causes round of errors. Yeah, so this is the bad thing here. So, okay, you have not given an answer on how to do this any better, but then you're very welcome here, because I'm now going to tell you. There's a more accurate summation. I mean, there are different algorithms to do more accurate summations, but there is one that is particularly simple. So, more accurate summation using, so what is important with this is that this way of doing a sum takes the same number of operations. So there are more clever ways to do it, even more accurately, but they need more operations. And what I'm using here is a way to use the same number of operations, like the naive one. And we sometimes call this thing the cascade, or pairwise summation. So, okay, before, have you heard about pairwise summation? Okay, no, then you're right here. But there's something in between. I have to tell you that is now pairwise summation is something very general, yeah. But now we use a pairwise summation specifically for Lattice Boltzmann, right? And Lattice Boltzmann has some additional constraints here. Yeah, so notice that the value of the least significant bit this is the thing that we call delta here, depends on the lattice direction. You know, this is because this is one of the important things that we have to know when we do the sum. Yeah, I just said summation is is the cause of round-off errors, in particular if you sum things that are of different size. And what you do is you sum these populations. And the populations are different size because the one that is going along the axis is more dominant than the one that is going in the diagonal. Yeah? So we have this lattice weights. So in D3, Q27, this is this W111. Yeah? This is the one that we also talked about before, is 1 over 216. The W101 is 1 over 54. So you see the least significant bit between these two is there are roughly 4 bits lost in between them. Yeah? Yeah? And you always have to use the least significant bit of the largest number you are dealing with is the one that we are talking about. Yeah? So summing these two up, there's already 4 bits lost. Okay? For the one going in the other direction. And this here, W10 is 2 by 27. And then we also have the one that is 8 by 27. So, which means there are different guys. So this would be larger than that one, and that one, and that one. So we have, so to speak, we have separate classes of directions. And the important thing you have to do is you always have to, if you do a sum, you always have to do the sum within one class first. And then when you have summed over one class, you can sum the classes together. Yeah? In order to keep this here small. So let's see how this would actually work out. And now we also come to the pairwise operation. So again, we compute M100, and I'll make a table here with this here being the step. So, and then we have the class, say, the class that comes with W111. Then we have the class, Then we have the class that has the weight W110, and then we have the class with W100. So, and now we have the step. So the step is the summation 1. So the first summation that we do. And this would, for example, be here for the class that have so these are the 8 guys in the diagonal. These are the 8 guys in the diagonal, right? So you would do a sum F1 JK minus F minus 1 minus J minus K. So what you do is you always sum the guys that are in opposite direction. Yeah, they are obviously of the same class, right? So this is how you start with. And here in this class, you will start with 2 different ones. 1, 0, K minus F minus 1, 0, minus K. And so there would be a different one, F1 J0 minus F minus 1 minus J0. So these you would use separately, and here would have F100 minus F minus 100. Okay, so these are the first operations that you do. And now you have to combine these guys. Now what you have to see is there are permutations. Yeah, because I'm writing here JK, yeah, so there are permutations of them. And these guys here have 4 permutations. Yeah? These operations have 4 permutations. Here are 2 permutations, so there can be K can be 1 or minus 1, and here J can be 1 or minus 1, right? So J cannot be 0, because otherwise it would be in the other class. Okay? And here there's only this 1 permutation. Okay, so what we see is we have 4 permutations in this one class, 4 permutations in the other class, and 1 permutation in the last class. Now we do the so-called pairwise summation. So the pairwise summation allows us to only sum over pairs. So if you do the loop, what you do, yeah, the naive computation is, yeah, you have a range of numbers, and then you take the first number, you add the second number, and then you add the third number to the sum of the first and the second number. Yeah? And so you go on. Yeah? So you accumulate on this one number. And the pairwise summation is you split everything in pairs, you compute the pairs, you sum the pairs, and then you take all the pairs and take new pairs of these pairs, and you sum these pairs, and then you sum the pairs until it gets to the last value. This is what we're going to do. So we'll add these 2, and we'll add these 2. And this is step number 2. We'll also add these 2 and add these 2. And here we don't add anything. So then we come to step 3, where we add these 2 and we add these 2. Then comes step 4, where we add this 2, and then finally we come to step 5, where we add these, and so we come to the M100. Now look, the naive summation, was naive in several ways. First of all, it did not take care of the different classes that we sum up, right? So actually, the round-off errors in between was switching backward and forward. But the more important thing was we need 18 summations, yeah, and we get 18 times the least significant bit as our error. Now, in this, each of we only have to add up the, so everything here goes only not to 18 summations, but only through 5 summations. Yeah, so we add up only 5 delta x instead of 18, or not delta x, delta x. So let's say, because, okay, go back. The number in the naive way, we had number of summands. Number of summands is n is equal to 18. I think I'm making a mistake. If you have to add 18 numbers, you have to have 17 additions, right? Yeah, okay, good. But anyway, so this, this doesn't make a big difference, naive summation. Say this is naive. So should I write, okay, it's probably 17, yeah? It's probably 17. So one more or less is not the same. And a pairwise summation, so there, how many steps do we have? So we have to build a tree, right? Yeah, and this tree has, and also with the tree we have to get the upper bound. So the tree has levels, a logarithm of 2 of the 18 or even 16, you know, before this doesn't make any difference because we have to take the upper bound of this. Yeah? The upper, the roof. So this is, we have to go through 5 steps in order to get all of them summed over a tree. So the error in pairwise summation is like delta log, so roof of the binary logarithm of the number of participants, probably the number of participants minus 1, but I'm not going to bother about this. And this is smaller than the delta times the number of participants. Okay, so this is the pairwise summation, and now we come to the last part of this lecture, and this is what we call the Chimera transform. So the Chimera transform, there's an interesting story behind this, because I remember the reviewer of the publication that introduced this meant that it's too trivial to be actually published. The thing is that the Chimera transform is the thing that makes a cumulant Lattice Boltzmann method feasible. Without this, it actually doesn't work. So we'll see what is this about. See, now in addition to computing, so in order to compute these cumulants, we have to compute a lot of moments before that, yeah, because then we can turn the moments into cumulants. So there's several steps. So we always have to do compute first moments, do the collision, and then again computing distributions or populations from moments. So the cumulant method requires a transformation from populations and we go to central moments instead of raw moments in the cumulant methods. So we have to go one way and then we have to go back. And every time we do all these sums, yeah, for computing moments. So, and then this means there is, again, such a naive transformation that looks like this. So the central moments, we write them at K as K, A, B, C, is of course the sum over I, J, K equals to minus 1, F, I, J, K of I minus U and minus U1, and I'll now consider this U1 as non-dimensional, yeah? Otherwise I would have to write divided by delta x, and so, okay, you know what I mean. By the power of A, J minus U2, by the power of B, and K minus U3 by the power of C. So now we have to compute 27 of these moments, right? And we have 27 populations, so 27 populations times 27 moments that we have to compute. So this is the expensive step in the algorithm, right? Yeah, the collision and so on is not so, but you get in with 27 distributions. Every time you have to sum over all the 27 terms to get all the other moments. Okay, this is the naive way of doing it, and we already learned that it's not a good idea to use naive summation. At least we should do pairwise summation, but there is something a little bit more clever than because there's also a naive pairwise summation, right? So you could also improve on this still. So, okay, let's say this is the most expensive part at all in the Lattice Boltzmann method because it has to be done so often. Yeah, most expensive operation in the method. So it is not necessarily if you do it once, it wouldn't be that expensive, but it has to be done so often. This is the thing. Okay, now the question how to accelerate it. How to accelerate this guy. And here comes the idea of a chimera into it. So a chimera is something that is part one and part the other, right? And the idea here is to use something that is part distribution and part moment. So what do we mean? Say there is K, I define now Kij. So Ij are the indices of the populations, yeah, in the distribution space. And I make a line here just to separate them. Yeah? This is not important. This is my own nomenclature because I didn't come up with anything better. So there's a line separating this, and the C is the index of the moment. Yeah? So what I'm doing in building this chimera by just summing over K. But just summing over K, Fijk, and here comes K minus U3, and this by the power of C. So there are, of these things, there are actually there are 27. You have to do this 27 times, yeah? But the summation goes only over 3. So once you have these guys, you can do the similar thing over the direction B. So we have already B and C, they're already here. And we do a summation now over, what is it, J? J is equal to 1. So over K, Ij and C, and this is J minus U2, and this by B. And again, you have 27 times 3. And then you come to the actual central moment, which is KABC is equal to I is equal to minus 1 and 1, and KIBC I minus U1 A, and again this is 27 times 3. So apparently this is completely trivial, yeah, to see that you can rewrite this like this. But it makes a huge difference because now you have to sum them up, and what you see is this is 9 times 27 terms. Okay, so the other was 27 times 27. So this thing is now at least 3 times faster, naively speaking. Practically speaking, it is actually 5 times faster. Yeah, it is. So when I did this first, I thought, okay, it must be 3 times faster. But the reality is it's actually 5 times faster, and this has to do with the fact that each of the terms that we sum up in the Chimera transform, yeah, because we are not, we're also not computing these guys again and again, right? Yeah? So they have fewer terms in each of the step. And they have fewer steps. Yeah? And this leads to the condition that since each term in the Chimera transform has fewer operations, than in the naive transform, the savings are even higher. Now, I was not able to compute this directly, so what I did, I used Mathematica to actually count the operations. So let's count the number of operations. So what came out with counting was for the naive case and for the Chimera case. So we count the additions. So there's 1,000. You see, this is not really a small number. Yeah, you do this once. You have 1,482 additions. Yeah, in the naive, and you have 270 in the Chimera version, and then there's multiplications on top of this. Multiplications with roughly the same number, 1,452, and here you have 162. So that's quite a difference in the number of operations, so which means that there's roughly now 1/5 of the operations. You see, this is already much faster, but we've learned something else. We should not only look at the speed, we should also look at the accuracy. And taking it apart like this actually leads to a pairwise summation, or something that is, it looks a little bit, the structure is a tiny little bit different, but it's actually a pairwise summation, or in the small parts where it's not exactly a pairwise summation, you can make it a pairwise summation. Yeah? And therefore, it's also more accurate in two ways. First of all, it's taking less operations, and it's also pairwise. It's also ordered. It's also important. It's also ordered according to the directions. So we got the pairwise summation. And this actually is more important, it's a funny thing. Actually what this is, yeah? And because we learned that computing a moment is a Fourier transform, right? And this here, what is this doing is a fast Fourier transform. The Chimera transform is a fast Fourier way of computing moments. And why is the fast Fourier transform called fast Fourier? Because it's fast, but it has a more important thing, namely it is also more accurate because it does pairwise summation. And this is more important, yeah, because the one thing just makes your code run faster, but the other one makes your code actually run more accurate, and this can be necessary because if you have 1,452 multiplications and 1,482 additions, in each update before you even do the collision, right? Yeah. So this destroys your accuracy due to a round of errors. And what we have actually observed is that, so we measured this, so no particular good theory, but a single naive transformation can lose 10 significant bits. And by I mean 10 significant bits more, not in absolute, but more than the Chimera transform. Ten significant bits is a 3, is a 2 by the power of 10 is 1,000, I believe. Yeah? Yeah, so you're losing in decimal numbers, you're losing 3 digits. You're losing 3 digits every collision. I mean, not incrementally, but not necessarily incrementally. And you keep 3 digits more in decimal digits, or 10 binary digits more if you use the Chimera transform. I mean, that's not necessarily always, but this wasn't a measured observation, so it does not necessarily always be like this, but it has been observed like this. Okay, little overtime, sorry. As always, thank you for listening.